Signals and Systems Assignment Help. For any assignment-related queries, call us at +1 678 648 4277. 678 648 4277. You can mail us at info@matlabassignmentexperts.com, info@matlabassignmentexperts.com, or reach us at https://www.matlabassignmentexperts.com. 1. Second-order systems. The impulse response of a second-order CT system has the form where the parameters sigma, omega d, and phi are related to the parameters of the characteristic polynomial for the system, S2 plus Bs plus C. A. Determine expressions for sigma and omega d, not phi, in terms of B and C. Express the impulse response in terms of complex exponentials. The impulse response is a weighted sum of modes of the form where S0 and the characteristic polynomial has the form. Thus B equals 2 sigma and C equals sigma 2 plus solving, we find that MATLABassignmentexperts.com. B. Determine the time required for the envelope of H(t) to diminish by a factor of e, the period of the oscillations in H(t), and the number of periods of oscillation before H(t) diminishes by a factor of e. Express your results as functions of B and C only. The time to decay by a factor of e is. The period is. The number of periods before diminishing a factor of e is. Notice that this last answer is equivalent to Q/pi, where Q equals MATLABassignmentexperts.com. C. Estimate the parameters in Part B for a CT system with the following poles. From the plot sigma equals 10 and omega d equals 100. The time to decay by a factor of e is 0.1. The period is the number of cycles before decaying by e is the unit sample response of a second-order DT system has the form MATLABassignmentexperts.com. Where the parameters are 0, omega 0, and phi are related to the parameters of the characteristic polynomial for the system. D. Determine expressions for R0 and omega 0, not phi, in terms of d and e. Express the unit sample response in terms of complex exponentials. The poles have the form z equals R0 e j omega 0 and z equals R0 e minus j omega 0. The characteristic equation is z2 plus dz plus e equals z minus R0 e j omega 0, z minus R0 e minus j omega 0, equals z2 minus 2 R0 cos omega 0 plus R2 0. Thus d equals minus 2 R0 cos omega 0 and e equals R2 0. Solving, we find that E. Determine the length of time required for the envelope to diminish by a factor of e. The period of the oscillations in H, N, and MATLABassignmentexperts.com. The number of periods of oscillation in H, N, before it diminishes by a factor of e. Express your results as functions of d and e only. The time to diminish by a factor of e is taking the log of both sides yields and ln R0 equals minus 1, so that the time is the period is 2 pi / omega 0, which is the number of periods before the response diminishes by e is. F. Estimate the parameters in Part E for a DT system with the following poles. MATLABassignmentexperts.com. From the plot omega 0 equals 10 minus 1, the time to decay by a factor of e is. The number of cycles before decaying by e is. 2. Matches the following plots show pole zero diagrams, impulse responses, Bode magnitude plots, and bode angle plots for 6 causal CT-LTI systems. Determine which corresponds to which and fill in the following table. Matlab assignmentexperts.com. Pole 0 diagram 1 has a single pole at 0. The impulse response of a system with a single pole at 0 is a unit step function, 3. We evaluate the frequency response by considering frequencies along the j-omega axis. As we move away from the pole at the origin, the log magnitude decays linearly, 5. The phase is constant since the angle between the pole and any point along positive side of the j-omega axis remains constant at pi/2. The angle of the frequency response is therefore minus pi/2, 4. Pole 0 diagram 4 has a single pole at s equals -1. The impulse response has the form S2, t equals e minus tu, t2. As we move along the j-omega axis, we move away from the pole at the origin, and the log magnitude will eventually decay linearly. Because the pole is not exactly at the origin, this decay is not significant until omega equals 1, 6. The phase starts at 0, and eventually moves to minus pi/2. Note that as we move farther up the j-omega axis, this system behaves like the system of diagram 1, 2. Pole 0 diagram 3 adds a 0 at the origin. A 0 at the origin corresponds to taking the derivative, so we take the impulse response of pole 0 diagram 4, 2, and take its derivative, 4. When omega is small, the 0 is dominant. As we move away from omega equals 0, the effect of the 0 diminishes and the log magnitude increases linearly. For sufficiently large omega, we are far enough that the 0 and pole appear to cancel each other, and the magnitude becomes a constant, 3. A 0 at the origin means that we take the phase response of pole 0 diagram 4, 2, and add pi/2 to it, 6. Matlab assignmentexperts.com. Pole 0 diagram 2 contains complex conjugate poles. The impulse response has the form which is response 1. The magnitude response will eventually decay twice as fast as that of pole 0 diagram 4, 6. Since there are two poles, there will be a bump at around omega equals 1, 2. At the origin, the angular contributions of the two poles cancel each other out, hence the angle is 0. As we move up the j-omega axis, the angles add up to minus pi, with each pole contributing minus pi/2, 3. Pole 0 diagram 6 adds a 0 at the origin, meaning that we take the derivative of the impulse response of pole 0 diagram 2, 1. The derivative ends up being the combination of a decaying cos, t, term minus a decaying sin, t, term, 5. The 0 at the origin adds a linearly increasing component to the magnitude function, 4. It also adds pi/2 to the phase response everywhere, 5. Pole 0 diagram 5 has complex conjugate poles and zeros at the same frequency omega. The system function has the form Matlab assignmentexperts.com. This denominator has the same form as pole 0 diagrams 2 and 6, but has an additional power of s, corresponding to differentiation, in the numerator. This leads to a response of the form in 6. The symmetry of the poles and zeros means they cancel each other's effect on magnitude, 1. The phase response at omega equals 0 is 0, as the contributions cancel each other out. As we move past omega equals 1 where the conjugates are located, the phase moves in the negative direction faster, but eventually settles back at 0 as we move farther and the contributions